Hi, thanks for joining me. I am back. I took about a month and a half break from making videos and uploading them to YouTube to focus on some exams that I had at uni, but those are all done now. Those have been completed. It's also the summer for me now, so I'll be able to come back to making videos and hopefully maintain that once every other day upload schedule. Anyway, let's jump into today's video. We have a cuboid with width W, length L, and height H. And here are the formulas for its volume, area, and perimeter. So volume is just length times width times height, so LWH. The area is just the sum of the areas of each of the rectangles on the face of the cuboid. So for example, here we've got WH is the area of this rectangle, and of course we've got an equivalent rectangle at the back here, so we get a 2WH here. And then similarly a 2LH and a 2LW, and I've factored out the two to give us the area. And then the perimeter is just the sum of the lengths of the edges around the cuboid. So we've got 4 lengths, the one you can't see there, and then 4 widths, and then 4 heights as well. Okay, and that gives us the perimeter. And what we want to know, is it possible for V to equal A to equal P? So the volume to equal the area to equal the perimeter. Now, if you ask perhaps a physicist or an engineer, straight away they'd respond by saying, no, it's impossible, because if you just consider the units, volume is in units cubed, area is in units squared, and perimeter is just in units. So it's impossible for them to actually be equal. However, for today's video, we're going to ignore the units and we're just considering the numerical value. So we want to know, is it possible for the numerical values to be equal? Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to jump straight into a solution. Now, to start off the solution to this problem, I'm going to start off by explaining and talking about something that seems completely unrelated. And what I'll do is, once I've sort of talked about it a little, I'll show how it relates to our initial problem and how we can use it to solve our initial problem. But what is this I'm talking about? Well, I'm going to talk about the discriminant of a cubic. So you probably have heard of the discriminant of a quadratic. So if you've seen quadratic equations before, you probably may have seen the quadratic formula. And the discriminant of a quadratic is that bit under the square root, so the b squared minus 4ac term. So, and if you studied sort of quadratics in any detail, you'll know that if b squared minus 4ac is strictly positive, then your quadratic has 2 real roots. If it equals 0, so if b squared minus 4ac equals 0, then you have a repeated root. But if the discriminant is negative, so b squared minus 4ac is less than 0, then you have 2 complex roots, so 2 roots which aren't real. Okay, and we have something very similar for cubics. So let's take a generic cubic equation, p of x, ax cubed plus bx squared plus cx plus d, where a, b, c, and d are just some real constants. Okay, and in fact what I'm going to talk about is the discriminant of a cubic of this form, but you can actually generalize this to higher degree polynomials as well. But I'll leave that perhaps for another day, or I'll try and find a good link so you can do a bit of reading after the video. Anyway, I'm going to define this thing here, which is just a triangle, but it's going to denote the discriminant. So I'm just essentially calling it this thing here. So it's a to the power of 4, so this number here to the power of 4, times x1 minus x2 squared, times x2 minus x3 squared, times x3 minus x1 squared. And here x1, x2, and x3 are the roots of p of x, which, just looking at this thing here, we don't know what they are, but we know that 3 roots, at least in the complex plane, exist, and that follows by the fundamental theorem of algebra. Now what we're going to do is this function here, which I've just called the discriminant, I'm going to show that this actually has similar properties to the discriminant of a quadratic. So we want to show that if this guy is positive, then our cubic has 3 roots, 3 real roots, sorry. If this discriminant is 0, then it only has 1 real root and a repeated root. And if this discriminant is negative, then we only have 1 real root. Okay, but firstly, let me just draw some cubics so we have a bit of, a bit of sort of background understanding of them. Every cubic has at least 1 real root. And we know that because suppose a is positive, then this guy here is going to be some positive number times x cubed. So then that means as x goes to positive infinity, this x cubed term is going to dominate over these terms, and oopsie daisy. And because the a is positive and x is going to positive infinity, this term here is also going to go to positive infinity. So as x goes to infinity, our cubic is going to look something like this. Okay, but as x goes to negative infinity, x cubed is also going to go to negative infinity. And because a is positive, that's not going to change the sign, so it's also going to go to negative infinity. And because this graph is continuous, it's going to have to cross the x-axis at one point. This isn't a very good, well-drawn cubic. It's got too many sort of weird turning kind of points, but you get the idea. If it's going to go to positive infinity and it tends off to negative infinity, there's got to be at least one point where it passes through the real axis, and that's followed by the intermediate value theorem. So this guy always has at least one real root, but of course it could have two if one of them is repeated. So it could look something like this. Okay, in this case it's got two real roots, one of which is a repeated real root, or it could have three real roots, which is a pretty generic case, but something like that. So one, two, three distinct real roots. So it can either have one root with a repetition, two roots, one of which is a repetition, or three distinct real roots. Okay, let me clean up the whiteboard and we'll continue. Okay, so now let's consider what happens when the discriminant takes different values. Now I'll leave it as a little exercise to you to prove that this discriminant here is always a real number, and if you want a little hint to how to prove that, just remember A, B, C and D are real, so it's a polynomial with real coefficients. So if we ever have a root, say z of p, so if p of z equals 0, then p of z bar also equals 0. So the complex conjugate of z is also a root of p. And then using that and the fact that cubics also have at least one real root, hopefully it shouldn't be too difficult to prove that this discriminant here is always real. But as I say, I'll leave that as an exercise to you should you wish to try and do that. So we have that the discriminant is a real number. Let's look at what happens in different cases. So let's look at the case where the discriminant equals 0. Oopsie daisy. If a discriminant equals 0, well, we're assuming that a is non-zero, because if a was 0, this would just be a quadratic, and we're not dealing with quadratics, we're dealing with cubics. So if the discriminant equals 0, then that means that one of these factors here, or at least one of them, is 0, but then that means we have a repeated root. So the discriminant being equal to 0 implies that we have a repeated root. And hopefully it's not too difficult to see that the converse also holds. If we have a repeated root, then let's say it's x1 and x2 are repeated, then that means x1 minus x2 is 0, so this whole thing is going to vanish. So we get that the discriminant is 0. So discriminant equals 0 if and only if we have a repeated root. Now what happens if the discriminant is negative? Well, then hopefully you can see that not all of our roots are going to be real. Because if all of our roots were real, then each of these guys here would be some real number, and when you square a real number, you're going to get something non-negative, and a to the 4 is obviously non-negative because a is real, so then that would mean that the discriminant is non-negative. But because we're assuming the discriminant is negative, that means that at least one of these is not real, and hence a complex, like a purely complex number, so something that's complex but not real. And then again, we have the property that if we have some complex root, which is not real, so suppose x1 is a root, and it's complex but not real, then we have that either x2 or x3 is a complex conjugate of x1. So let's just say it's x2, so x2 equals x1 bar, and then we also have that because we need at least one real root, x3 will be that real root. Okay, now this will give us, the discriminant being less than 0 will imply this, because again, remember we can only have either three real roots, one real root and like a repeated root, but the repeated root, this case has already been considered, or we have one real root and then two complex roots. So if the discriminant is less than 0, we must have two complex roots, and similarly, if the discriminant is greater than 0, then this implies that we have three real and I guess distinct, just to make it explicitly clear, roots. Okay, so the discriminant has very similar properties to the discriminant we're familiar with quadratics, because remember, if the discriminant of a quadratic is 0, we have a repeated root. If the discriminant is positive, we have two real roots, and if the discriminant is negative, then we have no real roots. So it's a very similar thing here, except if it's negative, we still have one real root, but the other two are purely complex. Anyway, these are properties of the discriminant. The next thing we want to do is actually express this discriminant here in terms of A, B, C, and D. Because right now, the discriminant as it stands, we need to know the roots. And that kind of, for the problem that we need to solve, it's not really going to help us. So if we can express this discriminant in terms of A, B, C, and D, will be good. But let's try and do that first. Okay, so if we just expand out the definition of the discriminant, so this is the definition of the discriminant, and if we just expand it out, factor a few terms, some things will cancel, etc., we get this line here, so it's equal to a to the 4 times this ugly something minus this ugly something else all squared. I'm going to call this first ugly something m, and this second ugly something n. So really all we want to do is compute a to the 4 multiplied by m minus n squared. But the way we're going to work out m minus n squared is actually to work out what m plus n is and what m times n is, and then using those we can then work out what m minus n all squared is. So let's firstly work out what m plus n is. So if we just look at these two guys here, m plus n is just this term plus this term. So let's just write that all out. x1 x2 squared plus x2 x3 squared plus x3 x1 squared. Then plus this guy here. So plus x1 squared x2 plus x2 squared x3 plus x3 squared x1. Now what we're going to do is group this term and this term together. So x1 x2 squared plus x1 squared x2. We can factor out an x1 x2 and we'll be left with x1 plus x2. So this is equal to x1 x2 times x1 plus x2. Similar thing for this guy and this guy. Factor out an x2 x3. So plus x2 x3. Then in brackets x2 plus x3. And then the final one, factor out an x3 x1. So plus x3 x1. Then in brackets x3 plus x1, like so. And then we can go ahead and factor this sort of once again. And notice that this is just x1 plus x2 plus x3 times x1 x2 plus x2 x3 plus x3 x1 minus, and the reason I have this minus here is, well, if you just consider this guy here and expand it out, this first term here, this x1 x2 times x1 plus x2 comes from this x1 plus x2 times the x1 x2 there. This x2 x3 times x2 plus x3 comes from x2 x3 plus this x2 times this x2 plus x3 here, and similarly x3 x1 times x3 plus x1 comes from this x3 x1 times x3 plus x1. But then we've got a few leftover terms which we have to take away. So when we get this first term, we're doing x1 x2 times x1 plus x2, but of course we've got the x1 x2 x3, so we've got to minus off one lot of x1 x2 x3. But similarly, when we get this term here, we're doing x2 x3 times x2 plus x3, and then of course we've got this x1 x2 x3, so we've got to subtract off another x1 x2 x3. Okay, and then finally you can probably guess what's going to happen now. To get this x3 x1 times x3 plus x1, so this thing times this thing and this thing, we're also going to get a plus x2 x3 x1, so we've got to subtract that off, and then we're going to get the minus 3 x1 x2 x3. Okay, so we've shown that m plus n is equal to this times this minus 3x1 x2 x3. Now you might be wondering, why on earth have I expressed it in this perhaps even uglier fashion to what we had up here? Well, because we can actually express each of these terms here in terms of the roots. So sorry, in terms of a, b, c, and d. And to do that, we're going to need to use Vieta's formula. Okay, so we just showed that m plus n is this guy here, x1 plus x2 plus x3 times x1 x2 plus x2 x3 plus x3 x1 minus 3 times x1 times x2 times x3. Now, Vieta's formula, if you've not heard of it before, essentially it just comes from taking our cubic, which we know is ax cubed plus bx squared plus cx plus d, and then also noting that the cubic can also be written as a multiplied by x minus x1 times x minus x2 times x minus x3. And then if you expand out that second way of writing it, so if you expand out x minus x1 times x minus x2 times x minus x3 with the a in the front, and then compare coefficients, you should then be able to write these guys here like this thing here. So x1 plus x2 plus x3, you'll then be able to work out is equal to minus b over a. x1 x2 x3 is minus d over a. x1 x2 plus x2 x3 plus x3 x1 is c over a. Yeah, but if you want to prove this rigorously, either do it for yourself or just look up Vieta's formula. Anyway, from this we can then work out what m plus n is, because it's x1 plus x2 plus x3, which is just minus b over a, times this guy here, which is c over a, and then minus 3 lots of minus d over a, which is just plus 3d over a. So m plus n is minus bc over a squared plus 3d over a, or you can write that as 3ad minus bc all over a squared. Okay, so that's how you write m plus n in terms of a, b, c, and d. And what I'm going to do now is just write down how we can write m times n in terms of a, b, c, and d. But to work that out, it's similar to how we worked out m plus n. you do these guys multiply together. It's a little bit more fiddly, but yeah, you use things in terms of the things we know about, so using Vietta's formula to your advantage to express it in terms of A, B, C and D. Anyway, let me clear up the whiteboard, I'll write it down and then we'll continue. Okay, so on the last whiteboard we showed that the discriminant is a to the 4 times m minus n all squared, and we showed that m plus n is equal to minus bc plus 3ad all divided by a squared. Now you can also show, as I said, but I haven't gone through the calculations myself, but you can also show that m times n is equal to this guy here. So ac cubed minus 6abcd plus 9a squared d squared plus b cubed d all divided by a to the 4. So another ugly looking term. Now we want to work out what the discriminant, and that's just a to the 4 times m minus n squared, but we can use the fact that m minus n squared is just m plus n squared minus 4mn. So if we do this guy squared minus 4 lots of this guy, and then multiply by a to the 4, if we expand out, take some cancellations and things like that, it all simplifies and boils down to this guy here. So our discriminant now is b squared c squared minus 4ac cubed minus 4b cubed d minus 27a squared d squared plus 18abcd. So a really long, ugly looking term, but the thing to remember about this is what we've done. We started with our discriminant here, which we had expressed in terms of the roots of our polynomial. Now we've expressed it just in terms of the coefficients of our polynomial, and that's what we want, because now we can work out the discriminant of a polynomial just by looking at it without having to compute the roots beforehand. Okay, so now let's use this to solve what our initial problem was, which was involving cuboids. Nothing to do with cubics or polynomials or discriminants or anything like that. Let's see how cubics and the discriminants relate back to the problem we initially had. Okay, so let's go back to our original problem. We asked the question, can these three quantities be the same? Now I claim that it's impossible, and the way I'm going to do that is by constructing or sort of proving it by contradiction, by supposing it was possible and then constructing a polynomial which just doesn't seem to work. Okay, so suppose for contradiction there exists some L, W and H that satisfy the original cuboid problem. Now remember that means because they're sort of lengths of cuboid, they firstly must be real, but they also must be positive. Now for this problem we don't actually need to worry about positivity, just the fact that L, W and H are real. Now from that I'm going to construct a polynomial which I'm going to call p of x, and in fact it's a cubic. That's what this whole video has been about, cubics. So p of x, and I'm just going to let it equal to x minus the length, x minus the width times x minus the height. Okay, now if we go ahead and just expand this out, we're going to get this is equal to x cubed minus L plus W plus H, x plus LW plus WH plus HL, also that's supposed to be x squared, x, then minus LWH. Okay, if that was a bit too quick for you, just pause the video and go through that yourself. But yeah, it's just basically looking at the coefficient of x squared. So how are you going to get an x squared? Well, you can take an x from there, an x from there, and then a minus h from there. That's where you get the minus h from. Similarly for minus w and minus l, and similarly for x and the constant term. Anyway, that's what this polynomial equals. But if we're going to suppose that these terms here, v, a, and p are equal, let's just say alpha is what they equal. So alpha equals v equals a equals p. But then, well, L plus W plus H is just p over 4. So that's just alpha over 4. So this is x cubed, oopsie, minus alpha over 4 x squared plus, now LW plus WH plus HL is just a over 2. So that's plus alpha over 2 x, and then minus LWH is minus the volume, so just minus alpha. So if we just multiply through by 4, so on the left hand side we get 4p of x, which I'm just going to denote p tilde of x, so it's just some new polynomial. That's going to equal 4x cubed minus alpha x squared plus 2 alpha x minus 4 alpha. Now we already know the roots of p tilde of x, it's just L, W and H. Now remember, L, W and H are real numbers. So from what we just showed about the discriminant, that means that the discriminant of this polynomial here must be positive. But what we're going to quickly show is that that is impossible. Let's quickly show that. Okay, so we have that p tilde of x is 4x cubed minus alpha x squared plus 2 alpha x minus 4 alpha. And we showed earlier that the discriminant we can write in terms of the coefficients of a general polynomial. So if we just plug in our coefficients into this sort of formula for the discriminant and simplify things out, we get that the discriminant of p tilde is minus 432 alpha squared plus 112 alpha cubed minus 12 alpha to the 4. If we factor out a minus 4 alpha squared and then put everything in brackets, we get that this is equal to minus 4 alpha squared times this guy here, 3 alpha squared minus 28 alpha plus 108. Now this guy here is just a quadratic in terms of alpha, and now we know how to deal with quadratics because we know about the discriminants of quadratics before. So the discriminant of this, we just work out b squared minus 4ac, and you can just work that out for yourself. You're going to see that this is negative, which tells us as this quadratic here, because alpha is a real number, this quadratic is always going to be positive. So this number this sort of quantity inside the square brackets is always going to be a positive number. Multiplied by alpha squared is positive, multiplied by 4 is positive, but then multiplied by minus 1 is negative. So that we have that our discriminant then is less than 0. But that is a contradiction because remember, we must have that the discriminant is non-negative because there are no complex roots. The roots are L, W, and H, all of which are real. And we've arrived at a contradiction which tells us that it's impossible to have a cuboid with the same volume, area, and perimeter. Thank you for watching. This has been quite a long video, but I think it involves some really cool maths and it involved the discriminant of a cubic. I sort of heard that there was a discriminant of a cubic, but I'd never been taught it at school or even at uni, and I thought it was pretty cool and something that I think will help solve a lot of problems. So if you haven't seen it before, I hope you enjoyed it, and I'll leave a link in the description below where you can find out more details about the discriminant for higher order polynomials. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.